Hello friends, welcome to engineering tutorial. So we will continue our discussion with the subject of electrical machines. So far in the previous videos we discussed some basic introductory concepts related to electrical machines, their basic definition, classification, then the various operating principles involved, such as Faraday's law, Fleming's rule, and also about the energy conversion principle involved in electrical machines and all the related concepts. So in this video we are going to study a concept which will be very helpful in understanding the operation of electrical machines, especially the DC machines, be it DC motor or generator. So this concept will come very handy to grasp those advanced things. Okay, so this will be the fundamental concept involved in it. So this concept which we are going to discuss today is linear DC machine. So first, what is a linear DC machine? Okay, what does it do exactly? So as I said, this is a very simple and easy way to understand the functioning, the principle of operation of all other DC machines, be it motor or generator. It has the same operating principle and shows the same behavior, okay, that by DC motors and generators, in general motors and generators. Okay, so a linear DC machine, the basic arrangement of a linear DC machine, it consists of a battery which is connected to a resistance through a switch, a smooth frictionless conductor which is free to rotate, and this conductor is placed in a constant uniform magnetic field. Okay, in that vicinity the conductor is placed. So the diagram, it looks something like this. This is the supply voltage, the battery. This is the switch connected to a resistance, and this is the conductor of length L which is placed in a magnetic field of flux density B, capital B. Okay. Now, in order to understand its operation, we have to take the help of certain mathematical equations which are based on Faraday and Fleming's rule and all the other things which we have already discussed. So I would suggest you to please watch the previous videos first, okay, and then come to this. Otherwise you can have some confusion. So please watch the previous videos. Okay, so there in this linear DC machine, a number of equations are involved related to the various aspects. So the first equation is for the force acting on the conductor which is placed in the magnetic field. Now if you remember Fleming's rule, it states that it has two statements. First, a current carrying conductor placed in a magnetic field experiences a force and tends to rotate. That's the first statement. The second statement is, if a moving conductor or a rotating conductor is placed in a magnetic field, a voltage will be induced in it. A current flows through it. As a result of that, a voltage is induced. So these are the two statements. So according to the first statement of Fleming's rule, the force which acts on the conductor and tends to rotate the conductor, the magnitude of that force, or the mathematical expression of that force, is given by BIL, capital B, small I and small l. Capital B stands for magnetic flux density, small I is the current flowing through the conductor, and L is the length of the conductor. Next is the second statement. Okay, a moving conductor in a magnetic field, as a result of that a voltage is induced in that conductor. The second statement of Fleming's rule. So the expression, the mathematical expression of that induced voltage in the moving conductor in the magnetic field is given by small v, capital B, L. Small v is the velocity of the angular velocity, or the velocity of the rotating or moving conductor in the magnetic field, and capital B is the magnetic flux density, L is the length of the conductor. So this is the expression for induced voltage. So this is the first equation, this is the second equation. Please write down these expressions along with the statements, because we will correlate them. First I am just stating what equations are involved, then we will try to establish a relationship between them, how one affects the other. Okay, so if we apply KVL equation to this circuit, okay, of this linear DC machine, if we apply KVL equation, it will look something like this: VB minus IR minus E and D equals to 0. The battery supply voltage, this is the voltage drop across this resistance, and E, I and D is the induced voltage. Now I have already posted a video related to how to apply KVL in a circuit, the two ways in which we can apply KVL. You can check out that video. So this is the KVL equation. So VB is the supply voltage, R is the resistance connected. This is the induced voltage. IR is the voltage drop. So this is the third equation involved. Okay. Then another equation is for the force with which the conductor moves. Now as the conductor rotates, there will be a change in velocity which will lead to acceleration, and we know that the force is equal to mass into acceleration. So this is the equation for the force. Because of the moving conductor, it accelerates because of change in velocity. So this is the equation for the force because of the accelerating motion. So this is the mass of the movable conductor, small m, and A is the acceleration of the moving conductor. So these are the four equations that are involved with respect to the linear DC machine. First, the force acting on the conductor in the magnetic field. Next, the expression of induced voltage because of the moving conductor, the KVL equation applied to the linear DC machine, and the force because of the accelerated motion of the conductor. Now, how to establish a relationship between them so as to explain the working of the linear DC machine. Okay. Sorry. So let at time t equals to 0, this switch is closed. Okay, at t equals to 0, this switch is closed. Now because of that, a current I will flow through the circuit, the closed circuit, a closed path is formed. Let that current be equal to I. Now we know that this is the KVL equation applied to the circuit. So the expression of I flowing through the circuit is given by I is equal to VB minus EIND by R. Okay, just we took I to the RHS, IR to the RHS, and then we determine the value of I. So we got this expression. Now at the start, okay, at time t equals to 0, this conductor is at rest, resting state, no movement, no motion. So as there is no motion, no velocity, velocity is 0, so the induced voltage will be 0, because initially the conductor is at rest, no velocity. So this will become 0, induced voltage will be 0. So if we substitute this EIND here, it will become the initial voltage, induced voltage is 0, and the current flowing at start initially when the circuit is just closed is I equals to VB by R, because the induced voltage is 0. If I substitute EIND with 0, the equation will become I is equal to VB by R. Now this current is now flowing through the bar placed in the magnetic field, this conductor placed in the magnetic field. So this current flows through this conductor. Now according to Fleming's rule, when a current carrying conductor is placed in a magnetic field, a force will act on it. That's the first statement of Fleming's rule, a current carrying conductor placed in a magnetic field. So here this conductor, a current I is flowing through it, it is placed in this magnetic field. So because of that, a force will act on this conductor bar, and this will be given by BIL. Okay, BIL we already discussed the first equation. So the force acting on this conductor is given by BIL. So this is what is called as the motor action, because here we are getting a mechanical motion. Okay, the definition of a motor is to convert electrical energy into mechanical energy. So this is what we call the motor action. A DC machine, you know, we never construct a DC machine with the intention of a motor or generator. When a DC machine is constructed, all the parts in a motor and generator, they are the same. Only if we reverse one thing and the other, it gets converted into a motor or a generator. So this equation is the basis for the action of a motor, because we are getting a mechanical output here. Now as the bar moves, okay, because the bar moves, a current carrying conductor placed in a magnetic field experiences a force, and that tends to rotate this conductor, this bar. So when this bar moves, it rotates, gradually it will gain some velocity, and then it will undergo change in velocity. The velocity will increase. It means there will be it has some velocity. So as a result of that, a voltage will be induced across the conductor bar. Okay, the second statement of Fleming's rule comes into play here. A moving conductor in a magnetic field gets some voltage induced across it because of that rotating motion in the magnetic field. So the expression for that induced voltage is given by VBL, velocity, flux density, length. Now here we are getting an electrical output. See, induced voltage, voltage is an electrical quantity. So this is the basis of generator, because the definition of a generator says it converts mechanical energy into electrical energy. So here F equals to BIL is for motor action, and EIND is equal to VBL is for generator action. Okay, see, both things, we reverse one and the other, it becomes a motor or a generator. Okay, so this is the generator. The same linear DC machine now behaves as a generator. So as this conductor, it rotates and rotates, it starts gaining velocity. Okay, as this velocity increases, the induced voltage will also increase. because B and L, they are constant. It's a constant magnetic field, so B is constant, length of the conductor is constant. So the only variable here is the angular velocity. So when this angular velocity increases, when this angular velocity V, small v, increases, the induced voltage will also increase. And as this induced voltage increases, the current flowing through the conductor decreases as per this KVL equation. Okay, as the induced voltage increases, the current flow decreases with progress of time. Initially, induced voltage is 0, it was 0, that's why initially the current was VB by R, the maximum value. It started as a maximum. As the conductor rotates, start gaining velocity, acquires the induced voltage increases and increases, the current starts to drop. Okay, now if we combine all of this, okay, all this phenomena, okay, the starting of the DC machine, current flowing through it, then a current carrying conductor causing the conductor to move, then a moving conductor gets some induced voltage. If we combine all of this, the net effect it has is that the bar, this conductor bar, it acquires a steady state speed. Okay, and at this speed the force acting on the bar is 0, because when it acquires a steady state speed, acceleration will be 0. When it acquires a steady speed, there is no change in speed with respect to time, acceleration will become 0. So when acceleration is 0, this force F net, it becomes 0, acceleration is 0, steady state speed, acceleration is 0, so the force acting on the conductor, it will be 0 because of the moving conductor. So there, this, at that point when it acquires the steady state speed, the battery voltage equals the induced voltage. Okay, the induced voltage and the battery voltage, supply voltage, they become equal. And we know that the induced voltage is given by VBL, velocity of the moving conductor BL. So because it acquires the steady state speed, that speed is called as VSS, steady state speed, the speed at which the induced voltage is equal to the battery voltage. Okay, so this conductor now rotates at this steady state speed forever unless some external force disturbs it. Okay, so this is the sequence of events from starting to the beginning. Okay, now there are various graphs associated with the various parameters with respect to time. So first is the plot between velocity and time. Now we know that initially the conductor bar was at rest. So velocity was 0. So see, at t equals to 0, the velocity is 0. Then it acquires steady state velocity. So the steady state velocity VSS is equal to VB by BL. If we take BL to the left hand side, it will come to the denominator. So the steady state velocity will become VB by BL. So see, the steady state VB by BL. So this is the plot of velocity with respect to time. Next, induced voltage. Okay, the same thing almost for induced voltage. At start when the bar was initially at rest, the induced voltage was 0. Because velocity was 0, induced voltage is VBL. As V is 0, induced voltage is also 0. So initially at t equals to 0, the induced voltage is 0. As time progresses, the induced voltage starts to increase and gradually it becomes this, the maximum value equal to the battery supply voltage, which is VSS-VL. So the maximum value of the induced voltage is VB equals to VSS-VL. This is the steady state induced voltage. Then the next parameter is the current with respect to time. Here it follows the opposite thing. It goes from maximum to minimum. In all these, it goes from minimum to maximum, means a steady state, but here it goes from maximum to minimum, high to low. At start, the current, because the induced voltage was 0, if we put E and D 0 here, the initial current was VB by R maximum. Now as the induced voltage started to increase, the current started dropping. So pay attention to this equation here and this equation. If we substitute E and D 0, it becomes VB by R, the initial current flow. Then as current started to, the induced voltage increase with respect to time, the current started to drop. Okay, so this from maximum VB by R, then it started to drop to almost 0. The next parameter is the force. Okay, so initially this force, as it is dependent on current, because the induced force, it is given by BIL. So initially, when the current was maximum, the force was maximum, and as the current dropped, the force also it dropped. So it follows the same trend as current. So see, the induced voltage follows the same nature as the velocity, because the induced voltage is dependent on velocity. Induced voltage is dependent on velocity. So both these curves, induced voltage and velocity, they follow the same nature. Now the force acting on the conductor and the current, they are dependent on each other through this equation. So they also follow the same pattern. Okay, so this is the whole concept of linear DC machine. Okay, so this concept comes very handy to understand the advanced concepts related to functioning of motor as well as generator. So if you understand this concept, if you have a good understanding of this concept, it will become very easy to grasp those concepts related to the advanced concepts related to generator and motor. So here we have discussed about the linear DC machine, the constructional features, the various equations involved with respect to the DC machine and the working principle. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.